Hello everyone. Today I would like to tell you about new query plans that Postgres is able to do in version 11 and that we'll probably learn to do to execute. We are going to review patches that are under development. They're all publicly available and belong to different authors. And at the end of the slides and outside we have the links to all the appropriate threads hackers circulation. They belong to different authors. I believe you can actually ask the questions after every single slide. What is query plan? As you know that SQL is a declarative language and we say what we need to get but not how we get it. Then the query planner uses the statistics, available resources, and other data information, selects the appropriate execution plan and algorithm. Then we see that query works slow. We add up some indexes, we rewrite the joins and do it manually. For this, we actually do the explain command in order to see why these queries work so slow. Then we see the tree of the query execution plan. This is made of simple blocks. Every table is scanned in a way, either consecutive scan or using indexes. Then in some way they join together using different types of algorithm. Probably do some sorting and grouping. The consecutive scan is not that interesting. Let's talk about index then. In Postgres, we have three different index scan options. Why do we need it? First of all, the tables in Postgres is not index organized. All rows are stored in a special page storage heap. And if we want to get the rows in an organized way and get it fast, or for example if we want to filter them out fast, for example the simplest example is with three index that can speed up equal or more or less. And then the way the Postgres chooses the index. The index itself stores key data only, but the row is stored in heap in the non-organized storage. The basic option is to use the simple index scan. Just give us the link to the next row in the heap. We actually send a line to the filter and it gives us the link to the next row. We go to the heap, extract it, then return it. This is the basic index then. There is another option, Bitmap Scan. It is applied when we get low selectivity of different queries and you need to pull a significant part of the table. In this case, there is no use to extract row by row because we read one page multiple times in a strange order, but we can actually use a different method, Bitmap Scan. In this case, index finds all the links to the rows we need and returns them in a special data structure, the so-called bitmap mark. Then we take this bitmark and pull the required rows from the heap. It is important to know that it's page organized and you can use it in a sequential input and output. Third option. This is the so-called index scan. It's when we have all the data required in index. For example, we can actually request key data only. If we need the key only, B3 index can actually return the key value on its own. We do not have actually to stay and wait for the The only problem with index scan that may arise is that the information row visibility is stored in heap. And if, for example, you don't have the vacuum process the page, so you don't know whether all the rows are visible, so you cannot use the index scan. You need to go to heap and ask for the visibility information. Are there any ways to use this index scan more often? Because it really helps to save at input and output. In version 11 we have a nice feature covering the B3 indexes. This is B3 index, where the index may contain not only key row column but also additional columns. And if, for example, we have the index for primary network and you do some join often and you want to actually return a few columns, you can add them into the index as additional columns and you can get the index scan then. What are the advantages of this approach? First of all, you still have unique constraint running. If you have only the index, you can add an additional column to a key index. For some data type, we don't have the B3 operator. These covering indexes resolve these issues. You may have one index that will be constrained and actually can use it to do the index scan. Let's see the way it works. I have a table here, the hacker's mailing list. It's just a normalized table. They're just taking the ID key, the message sent date, author, text body, and actually the column for the full text search. We have the primary key index. But let's model joint that actually takes 1/5 of the table. It just contains 1 million rows. The size is a few gigs. Let's take the select and take 1/5 part of the table, and let's experiment how much faster the index scan. You can see that it triples the speed of this query. That means that it's quite a useful optimization. This is as for the index scan, but let's talk about the bitmap scan. Can we apply it to our task? Because some problems, some indexes do not contain or do not support the bitmap scan. For example, the index scan works only through the bitmap scan. For example, we may want to use a type of optimization in order to save time on input and output operation. Oh yes, there are some. For the time when we need to do the bitmap scan, we can actually do this using indices. We can do this without going to heap. This may be useful if we need to calculate the search results, if you know to count the page count. Nowadays they do explain, take the estimate number of rows that is calculated by statistics. It works more or less plus or minus 20%. But now in version 11 we get a way to do the calculation in a fast and precise manner. Bitmax works the following way. Index returns us the specific structure for B3 maps, and for every heap row we get 1 or 0, 1 if it matches the conditions and 0 if it doesn't match the condition. If we need just to calculate them only, we can actually add up the ones. But we have here a condition. We need to know about the lines so that all the lines can be visible to all the transactions. We shall not have long transaction, and we need to actually apply vacuum here. Let's actually consider the full text. We have gene index for the full text search, Multicolumn RTS. It's a specially processed index. We're going to look for the rebase word. and we would count the number of matches. And we can see that when the vacuum has not been applied, this optimization is not working because we need to go to heap, look through different new pages, and work slower than as compared to vacuum processor, because after vacuum we don't have to go to heap and it saves time. There is yet another important thing, the structure of the bitmap. It may be large, and if your working memory is not large enough, because on default this size is quite small, then it switches to the loss format. You will have the ones not for every line but for every page, and in this case we cannot count the number of lines matching the requirement. And this means that you need to increase the work main. In explain, you can nail this from the buffers line. If you just write the analyze buffers, it shows the number of pages we read. You can easily see whether we are there or not. Yet another interesting optimization that is now being developed. It is not in any version. We're discussing now circulation. Index gives some. It's the algorithm that takes B3 index and gets a unique value. Sometimes we get a case and people ask us to do this. We have a prototype here, but let's just use a synthetic test. There's a table with one column, 100,000 lines from 0 to 500. It means that we have only 500 unique values. If you select this, so how do you organize and sort it? It just sounds and on top we get the knot that will process the double entries. It means that we will read through local types, because otherwise we could use the tables and immediate the similar values. But if we try to use the index and apply the algorithm, that we can see that the time goes down significantly. Yet another interesting algorithm for B3 index that is being developed, KNM. This is the K of the nearest neighbors. We have the gists now, and all gist index already support this. If you just had to count and search for the KNM using the GistLR image, we have the supporting GistLR indices. You can install it, but actually it takes more time to process. You have just more time, to update as compared to the B3 index. Therefore, we have a batch that executes the situation, that actually executes the feature for B3 index. Everything works really terrible without index. It just reads all the data, resource all these through different operators. The measure is we select 1000. We just want to resort all the 300 applications that we actually had before the 1st of March. We settle everything down before the date, and we just extract all the data, we sort it, and then we come to the limit. With the B3 gist, we speed up 200 times. And actually, with this type of optimization with column B3, we speed up even more. Yet another interesting thing, if we switch to the data sorting, we also have an interesting patch, incremental sorting. Why do we need to sort it all in our database? There are a lot of reasons we can use it for. First of all, this is order by, distinct can be counted by the sorted data, grouping, window functions, and merge and join. It also requires the sorted data. We do sorting quite often, and it's nice to speed it up. We have the following problem in Postgres sorting. If you have a specific blend that returns sorted data almost the way you need it, for example, sorted by column 1 but not by column 2, it just looks like we can sort it again. But Postgres is not able to do this, it just resources it from the scratch. And it is not always efficient. This patch is designed to add the incremental sorting. If, for example, you have the table sorted by column 1, you can use less memory and sort it by other columns. This is important when the leading column used to sort, you have the index, when it's not really unique, when it groups your data. For example, we have the index by subject. For example, we have a few dozens of messages per subject, and it looks like if we take a message sorted by subject, then we want to sort it by send date. Then we need to sort it furthermore, but within one group by specific subject. We do not need to sort all the data together because everything is sorted by subject. Then we do the in-group sorting. This helps us to save a lot of memory. This query, we want to, we want actually to see we want to extract and pull the time of the last message sent. That's why we need to sort it by subject, by date. Usually, the usual sorting pulls all the table, goes to the external merge. That's like 1 or 2 gigs. It works 22 seconds. And the incremental sorting above the index, as it sorts everything by group, it actually requires 2 megs of memory only and works 4 times faster. It's like one case when we can easily use the incremental data sorting when the data is grouped by the first column, and then we can regroup it by using different other columns. For example, we're talking about this type of limit. If we use the limit, we can save the process in multiple times. It looks like that we need to sort only a few first groups by the subject we get from the index, and we do not treat the most part of data. That's why we save a lot on the input and output time. Yet another important thing with sorting. Depending on the column order, the cost may vary. It is important when we do the combine, we could actually select the right order of columns in order to sort them, and it will be much cheaper. Postgres is not able to do it now. It actually does the sorting in the order of the columns. Here's like a synthetic example. We have the column with figures. It has a lot of unique values. And there's a long table with the strict one. It's quite expensive to compare it because it starts with the spaces. It has 60 spaces, and in Dawn it has some differences. So it would be nice to save everything by column 1 that is cheaper to combine. And then we can compare it with a more expensive column. It's just the patches that is trying to use 2 different sorting options and selects the cheapest one. You can see that the sorting time may be significant difference. The difference may be double. It just checks the unique columns, then it just checks the non-unique, and actually the time is 2 times less than is compared when we're trying to take it, in a different way.
Давайте поговорим про...
Now let's talk about connecting 2 tables, how to choose the order of joins, how to choose the right sequence of joins. In Postgres there are 2 main algorithms. First one is system R, which is pretty old. It's a dynamic programming algorithm that chooses the best one. It finds the best join for two tables. Then it combines the best joins it found for n minus 1 tables. It's very good, but it goes through too many combinations, and if you have a lot of joins, you can't deploy it anymore. That is why in Postgres, if there is a certain number of joins, it switches to genetic algorithm. It's a heuristic algorithm that doesn't try all the joins, but gives you very decent results. Okay. The common problem with joins is bad selectivity. Poor selectivity estimates for multi-column join on correlated columns. Very good example, columns that are just equal, a million of equal columns. And if we join columns A and B, Postgres calculates selectivity for one table and then just multiplies with the selectivity of joins for the second column. Since they are dependent, the result is completely wrong and it is 4 orders off. There are different ways around. There will be a talk about machine learning algorithms that can actually establish a back dependency, and also you can improve statistics for these joins. For example, if we join several columns, we have a certain index and we can create multi-column index. We can create some statistics on it by using composite values. And we create statistics not for A and B separately, but for A and B altogether. And it happens that it allows you to improve selectivity very much, and with this patch we almost hit the target. It lays in hottest patch. Well, in fact, this is a very interesting topic, since we do have, when we just have select, not join, we have special create statistics with dependencies. So if we had select with when A is less than 100 and B and less than 100, and we create statistics with dependencies, the selectivity would be right. But for joins, this stats is not enough, and that is why the development is on the go for real multi-column statistics, and this is a more it's an easier solution, a simpler solution for it. In fact, joins is a very expensive tool, and the less you have it, the better, because planning can be very costly. We're trying to minimize them, or at least to discard them at all, but at least there are very important cases when you have to use join. It comes to optimization and to joins with a very unique inner side. It means that on the inner side there is at most one row matches the join clauses, and it means that join doesn't introduce duplicates into rows. It allows you to do the following. We can skip materialization in merge joins. It means that each inner side tuple go only once, we never go back, and you can skip materialization, which is cheaper. When it comes to semi-joins, it's when we where exist, And like inner, it works like inner, but it doesn't have inner columns and it skips duplicates. And in this case, we can benefit from reduced inner join when the inner side is unique. And it makes our life easier. This optimization exists since version 10. Also, another very interesting case, which is not implemented yet, but still it's under development right now. It's self-join on primary key tables. It happens very frequently in ORM-generated queries, and also it happens when you are reusing complex views. And when we have several views like this and we would like to join them, we can come up with problems. Like we have a couple of views for our archive. The first one selects all messages from where subject is like P, and the second view selects messages for 2010. And when we would like to join them, we have this kind of join, which is in fact not necessarily at all, because we're using PG list on primary key, and theoretically we can discard it and substitute with scan and certain filters, and there is a patch that makes it all. It is looking for these joins, it discards them, and it replaces them with a scan on a primary key. It's just a scan on PG list where subject like P and sent between 2010. And it can accelerate your queries and your planning by several times, because planning is always very expensive. Now, what about outer joins? Outer join is a join when you get output on all outer rows, nulls for inner rows when none match. You can't replace them very easily like inner joins, and we would like to remove them too. There are certain optimization that allows us to do it. Okay, so the first example, we decided to join our messages in threads. In order to do so, we just put the table aside with the same key and with the parent message. Then we would like to denormalize it. We right select from PG list, left join parent message. It's a normal query, but then we filter it. For example, we would like to have all child messages for 42, and this left join is not necessary anymore because we have a limitation for this string. Left join can be reduced to inner join, and Postgres can do that, and we have inner join instead of outer join in this case. What else can be applied? It happens that when outer join is unique, inner join is unique and is not used, so we select PG list. Since we know that the inner side is unique, it will not introduce any duplicates, and since the join is left, strings will not disappear. It happens that we can just discard the join. This optimization exists for quite a while, and also there is an interesting case when join is not for a unique column. We join on condition id equals parent, and parents can be equal across different messages. That is why some strings can be duplicated, but when we have distinct In this case, duplicates will be removed and join can be removed too. But this is under development for a moment. What algorithm of join execution exists? There are three of them. Nested loop, merge join, and one more. So first, it's all about sorted join. We can join them in a linear manner. Also, there is a very interesting patch that is implementing merge join on a range overlap. For example, now we can only work with equals. This is the example on range overlap. Just a synthetic example. We have 100,000 intervals in for range, and they overlap pair by pair with these ranges g plus 10 and g plus 15. How can we join them on range overlap? Maybe the easiest option is to have a gist index to calculate it very fastly. And on top of that, we have nested loop join. So for one table we have sequential scan, and for another we have scan with range overlap. It works, but it happens that if we sort these ranges and apply this modified merge join, the performance increases by several times. You can see the figures with merge join over sort. The time is 3 times faster. If we have B-tree index, it's even faster. But B-tree is not always helpful when it comes to ranges, and it's under development right now. A very interesting patch that will be committed in version 12. It's about inlining of common table expressions. It's all about complex queries when you would like to get some logics and read it somehow. But in Postgres there is a very interesting thing that all CDEs is a barrier for optimization, because it doesn't go to the main query and it is calculated separately, and it's not always good. Let's have a look at the example. Very simple example. We have a CDE that calculates number of messages across all subjects, and then we just decided to filter it with the subjects starting with P, the most popular ones. And the plan is very bad because predicate doesn't process like CDE. Then first we calculate number of all messages across all subjects, and then we filter it. It's very time consuming, and the plan is bad. And the second problem, apart from predicates, is that we are losing stats in this case. When we are looking at base relations, the planner knows stats, and when it goes through joins or CTE, the stats is only by default. It may lead to unoptimal plans. We see that the stats estimation is bad. 400 rows. We think that it will get us 400 rows, but in fact they are 15,000. But now we have an option, and it will be committed in version 12. So we can just write with as materialized on off, and in default we inline it if we have only one link. If we have several links or it's a gold function, it's not clear whether to inline it or not. That's why we don't inline. If we have only one link, we always inline. Yes, if materialize on, we don't inline. So this case, when we're using CD deliberately for optimization, it will stay. And if we deliberately inline, we always inline if it is possible. If there are no side effects like select for update or recursive or goal function. So we have to patch like this, and in this case, if we enable inlining, this city is processed like a sub-process. We put this predicate, and then we index scan it. It works several times faster, and we get a decent assessment of rows, plus minus 20%, but that's okay. So we have a patch like this. And finally, a couple of interesting patches that optimize functions pre-calculating. Let's have a look at a couple of examples using full text search. So we have totals query that convert our query into something suitable for indexing. And this function has two options. The first one is with one argument where we have the query itself. It is stable. It happens because we have unclear parameter like full-time search parameter like English language. It means that the value of this function can change before committing, and we cannot inline it. And the second scenario is when you push the configuration explicitly and it is immutable. And we can inline it on the level of planning. And there are two patches, first for cache stable functions in expressions at execution time. So we have a query like this, just full-time search. We have genindex for this. Queries go through bitmap hit scan. And also there will be a recheck because data can be not very correct. We have to check the predicate. And at the stage of recheck, Postgres always recalculates the value of this function. And it happens that if we cache it, so just we save 25% of our time because we don't have this constant recheck. How we can actually fight with this? We put it into form list like in this query, and then we have nested loop join over function scan and bitmap heap scan, and then it caches this value, and it's okay, but we can make it even better if the function is immutable. If it is immutable, we can just discard this join and inline it at the planning stage. And when we have no join, it's always better because we have faster planning and we have better cost estimates, and this is the second patch under development.
So this is all I would like to say about the patches. How can we actually promote and influence the things happening in development if you're not a developer? Well, frankly speaking, there are a lot of things you can do even if you do not program on C. if you don't know the internal architecture of Postgres. The most important thing is testing of the efficiency, productivity, and casing. Very often, for some features, you lack some real cases where they work okay or where we have some problems and challenges. So, it's like the overall review that is not related to different productivity. You can talk about the cases, syntaxes. A lot of people enjoy discussing syntaxes. This is always useful. That means that if you're interested in patch, you can actually do some tests and give us some data. It works okay or not okay. It is always useful. That is all I would like to tell you. So thank you for your attention and time, and I'm ready to answer your questions. No questions. Thank you very much for your presentation. I have a few questions for just regular people. What do you mean inline in different contexts? You just sounded inline for CD, and I realized that we do the convert of the software convert. Yeah, that is right. Absolutely. It's immutable functions. We actually get the function at the predicator. Right. It is calculated at the planning stage. So this function scan, if for example we get this query in the from list, it will be the not a function scan. You can actually drop it out and replace it with result. The not that actually returns the constant value. Moreover, we actually get the Bitmap Scan. So in from we are going to have the messages only. Yeah, right. It is dropped from the from list. Where will the not result go to? Result, I didn't say it correctly. It will not be the result, but the value will be calculated at the planning stage and will be set to Bitmap Scan. Yet another thing, have you actually assessed the efficiency of the stage by stage, the join efficiency? Did you do the push and play and join of two tables? You assess the value. I'm not doing this, but this will be the Gatsima on the extension. We have this approach, and a lot of people are using this, but specifically for our case, the Postgres Pro as a more general solution. It's just a system based on machine learning that is trying, to run different queries and predict everything possible. Yeah, we've been having it for a long, long while, and it's working okay. Okay, do you mean that it produces better selectivity? Yet another question on the estimated software cost. You said that on default we sort the columns in the order they are indicated in the group by. But in this case, we didn't have the group by, where we use the V column, the most expensive one. It is not stated here, but this is the sort time for the V column. I actually didn't write the query for the second time, but do you understand that the validity of this first thing is that you use the calculation only? Should we have the select of certain values, for example max, min, and we will stand on the first position, then this would not be an efficient optimization. This all depends on your queries. There are some queries when you need the specific sorting. For the group by, there is no actually great difference. You can do the test. That is all. Thank you very much for your interesting presentation. Thank you for your presentation. So, do you have any Bitmap patches? You just said there is a patch will be committed in 12 on version 11, on version 10, on version 9. Well, the feature set for the released version, the main action goes to the stability. There is some planning change, but it's for the backs only. So nothing will be backpatched for the previously released versions. We have our interest in enterprise version where we try to implement all the patches on an early basis. For example, covering indexes were committed, a year or 2 years before they got in vanilla. But vanilla doesn't backport anything. Thank you very much for your presentation. And as for the last slide, in clause 2, starting from what version can you do this? This is under development. So everything is under development, right? Absolutely. In my slide, in this corner I have the dev or released version. So dev means that it's under development. Thank you for your presentation, but are there any type of optimization for inherited tables? Now it's quite an active matter, but in partition, we do have a lot of planner changing in order to do the correct planning with inherited tables, but I'm not good at this, and that was the reason I didn't talk about it. It's a separate matter, separate topic. Yet another question. On one of the slides you just said will include, and you demonstrated the 3-time improvement. Are you talking about the covering index? Yeah. Do you understand correctly that it just, the sub-index gets more complicated? Yeah, that is correct. For example, the B tree, we have additional columns that we have in code. We just, pay the index cost with this side. What's about this index servicing? Is it more complicated? Servicing is not more complicated. For example, if we don't have the include index, we actually do the indexes, pull ID, and the second index for ID and subject, not include but a regular one. And sometimes it is more convenient as you do the index scan. But here we can actually use one. Yeah, of course. Servicing is more expensive, but it should not be more expensive as the structure and search structure does not change. We just add up additional data constant to every list. Yet another question. Do you have any promotion on parallel search scan? What about the by source join? Yeah, it's developed. I'm not actually keeping track of the parallel development, but I can tell you for sure that the benchmark of everything here, you actually have to switch off the parallel querying. Hash join, for example, are in parallel. Hash aggregate is in parallel. Something else? Yeah, that's cool. If we don't have any questions, thanks for your attention.